let's talk about the general function f of x. And we'll just play with, we'll take e to the x as an example. E to the x happens to be the easiest one next to that 1 over 1 minus x. And the assumption is there is some kind of polynomial that will mimic this, at least within some interval of convergence, within some interval. It may diverge outside of that, as we saw in previous one, like between -1 and +1, and we don't know where this thing converges, but say we have some kind of polynomial. Let's just write one more. Unlike previous case, these are all different coefficients here, right? In previous case, it was the same thing, but now there's no guarantee, because in order to generate something complex as e to the x, we cannot assume these are all same. And then, of course, we know what x's are, right? Okay, so now we have to figure out what these little things are, because we know that polynomials, and then we can figure out what e to the x is made of, and we can write a program. Okay, let's just think about this. And I want you to do it exactly this way. On the quiz 2, which is a take-home quiz, there is a Taylor series formula in your book. If you use it, it's -10 point each. You've been warned on the recording. You have to do it this way and this way only in order to get any kind of credit. Otherwise, you just get -20 and that's it, out of 50 points. You've been warned. Let's just evaluate this function as 0 and let's see what happens. So e to the 0 is 1 here, right? And let's see what we have on the right hand side. This plus, x is 0. Oh, they all die. So this is it. So at least we figured out one term. A0 is equal to 1. How about that? Okay, 1 down. And we have infinitely many more to go. Okay, now, how do we figure out the rest of it? This is a trick. We take a derivative of this thingy. So derivative of e to the x is still e to the x, good. But if we take derivative of the polynomial, that's very easy to do. This thing dies, so we have a1 plus 2 a2x plus 3 a3x squared plus 4 a4x cubed plus ... right? Okay, we'll evaluate this thing at 0 again. So this thingy becomes 1 again, and we have a1, and then rest of them die again. Whoa, we figured out a1. Can they all be 1? What do you say? Of course not, then it's same as previous example, right? So no, but we got 2 of them. Should we have some kind of, oh, I think we have, with a different color, black, I think we should have this thing running thingy going. So e to the x is at the moment 1 plus 1 times x plus, and then we'll keep this thing going, okay? Okay, now, then we take another derivative, double prime of x. So that's why e to the x is one of the easier things to figure this thing out, okay? And the right hand side, this dies, so this thing dies, so we have 2 times a2, x becomes 1 at the derivative, and now we have plus 3 times 2. Let's keep it like that instead of multiplying it to 6 for bookkeeping reasons, because we have to see the pattern really, really fast. a3x plus the next one, 4 times 3, a4 x squared and ... correct? And then guess what I'm going to plug in for x? That. So it's still 1. and we have 2 times A2, and the rest of them still died, right? So A2 this time is equal to 1/2. So, oh, we see something now more interesting. Okay, let's box that in. With me so far? So in our total, we have this, x squared over 2. Good? Say yes. Okay, then let's go one more. F triple prime of x. So there are 3. Triple prime of x. So e to the x being our favorite function for this kind of reason. And the right hand side, this thing dies now. So I have 3 times 2 times 1. Are we seeing a pattern developing? 4 times 3 times 2, A4x. Somebody tell me what the next one should look like. 5 times 4 times 3x squared, and dot, 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 like that. Who's confused? Y'all with me? And substitute 0 again. So this thing becomes 1. Is it 3 factorial? What do you say? Oh, I forgot A3. Hold on. I'm gonna put it in. Right? These are not factorials yet, but at least that one is, right? So does that tell you A3 is 1 over 3 factorial? What do you say? Do you believe me? Do you not believe me? Wait, was this factorial after all? 2 times 1, right? 2 times, yeah, this was factorial too, wasn't it? Wait, was this factorial? Yeah, 1 over 1 factorial. Okay, let's go back in and add those in. So this was 2 factorial, and the next term is x3 over 3 factorial. God, do you see the pattern? Guess what the next one? What is the next one that we want it to be? We're going to verify it, but don't we want this? Well, maybe we should do just one more to make sure, right? Let's do it. So f, oh, what's the fourth derivative? What's fifth derivative? I mean, up to triple prime is okay, but like, what's the fifth derivative? What are you gonna do? Do this, 1, 2, 3, 4, 5. Ew, there's also a Chinese version, 1, 2, 3, 4, 5. Okay, those of you who recognize Chinese characters, you know what this is the equivalent of, right? That thingy. What is a good notation to take this like high-powered derivative? Okay, Newton didn't have any of that, so he just did this, the boring. So when you put 4 superscript in a parenthesis, that means it's a fourth derivative, okay? I mean, we can tolerate triple prime, but after that, it gets really, really confusing. You know what I'm saying? You don't want to have 7th derivative, 7th prime, right? So we do this. And that's there, e to the x. And this now, this one dies. So next one, 4 times 3 times 2 times 1, a to the 4th. You get it? The next one is about to become 5 factorial. Oh, so when we substitute wrong color. When we substitute 0 again, this still becomes 1, and this is 4 factorial A4, and the rest, the x's all become 0. So that tells you a to the fourth power is equal to 1 over 4 factorial. And now we see the pattern, right? So we can say dot 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 and dot 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 here. A to the n power is equal to 1 over n factorial. You know what I'm saying? Are you with me? So we go up here. Oh, not there. Went too far. Here. This thingy. Let's put this in sigma notation now. So e to the x should be sigma of, tell me what to write. What do you want to start n from? And we have to have something like that over, oh, come on. From 0 to infinity. Told you most series in this business starts from 0, and this is why. Do you believe it? No, you don't, right? It's like, are you kidding me? Okay, let's see the graphics. Okay, I'm gonna have a new. Okay, first I'm gonna graph e to the x, which looks like this, right? And by adding those polynomials, could we really generate this thingy? We shall see. Have your calculator ready, so I need to have a factorial values, okay? So for the dramatic purpose, once again, I like to start with one term at a time. Okay, that failed spectacularly, right? These are not even same, but it still nailed it right there at one point, right there, 0, 1. Okay, we'll see. We'll add more terms, so plus x, right? Nah, not that impressive, right? Okay. And then plus x over 2 factorial, right? What did I do? X squared over 2 factorial. Good. Oh, actually it's remarkably good from about here to here, isn't it? Dang. Okay. And we have infinity. We only have 3 terms, and we have infinitely many more terms to go. Okay, x cubed over 3 factorial. I think I can do that much. 6. What? X cubed. Did I do 3 cubed? Oh my god. X cubed, x cubed. Wow, look at that, huh? From here to about here. Okay. Should we add 2 terms at a time now to save time? 3 terms at a time? Yeah. Okay, have calculators ready, standing by. So plus x to the 4th power. What's 4 factorial?
24.
24. You just have to need to multiply it. Yeah. Plus x to the 5th power. Calculator standing by. Somebody tell me what 5 factorial is.
120.
120. Yeah, that much was still not that bad. Let's do one more term. Plus x to the 6th power over
720.
720. Okay, shall we look at this much? Whoa! Wait, we passed this -1 to +1 already. Because the previous one, the interval of convergence was -1 to positive. We're like up to here, -2, and this side looks really, really good beyond 2. And we have infinitely many more terms to add. Let's just add 3 more terms, then you will be believers. So we are on x to the what power? 6th. Yeah. So we'll do plus x to the 7th. Somebody tell me what 7 factorial is.
5040.
5040. Okay. And plus x to the 8th over
40,320.
40320, like that.
Mm-hmm.
Okay, and then let's do one more, right? Plus, we are on 9, right? X to the 9th over, just speed up digits. 3688.
Oh, wait, no, sorry. 362.
Hold on, 362
80.
880.
Mm-hmm.
That.
Yeah.
Okay, we'll stop because calculator will overflow pretty soon. So it's like these denominators are getting big. Whoa. Maybe we are kind of pushing this thing towards out and creating asymptotic behavior up, down. You guys know why this side goes up and down, and this side looks really, really, really good. Let's zoom out. You see how good the other side is? My God, are you a believer? Do you believe? And guess what the interval of convergence of this thing will become if we have infinitely many more terms? Could we push this thing out to infinity? We shall find out, eh? Dang, no, this is impressive thing, isn't it? Okay, and we'll find out the interval of convergence now. Okay, in order to figure out interval of convergence, we do the ratio test. Limit n approaching infinity of, and our terms looked like this, right? You know what I'm saying? Our sequence inside the series just looked like this. So we have x to the n plus 1 power over n plus 1 factorial close absolute value. And we need this absolute value because x could be any number all the way out to infinity, excluding infinities themselves. So this thingy, do you see that? Let's cancel the factorials first. Do you agree that this is how you cancel factorials? You want me to review how to cancel factorials, or is this good? Okay, and then x's, there's an extra x, but be careful, we need absolute value, right? Because factorial, I mean, the n is positive, so we're okay, but we need that. What is this limit? Because x could reach out all the way to infinity here. Somebody answer that question. X could be any number, potentially all the way up to, but not equal to infinity, and n is approaching infinity. So, whoa, which one wins this race? This is equal to 0 as long as x is not equal to infinity, right? If x is equal to infinity, then we have a problem, L'Hopital potentially, right? So what does that tell you about interval of convergence? X not equal to infinity, you get it? How about that? All real numbers, because real number does not include infinity. Infinity is not a number, you get it? So as we suspected, this thing converges everywhere. My God, that is impressive now, isn't it? You get it? We'll do one more. and we'll call it a day. Only have 5 minutes left, so if I run out of time, you guys can quietly go, okay? Say g of x equal to sine x, and then we are still assuming there is power series that mimics this. Okay, we do exactly the same thing. So first, I'm going to plug in 0. This thing becomes 0 now. And this is a 0, and then everything else dies. So that tells you first term is 0. Okay, that's a nice start. Good. I'll go a little faster. So now we take a first derivative. Now this becomes cosine of x. And this becomes a1 plus 2a2x plus 3a3x squared plus 4a4x cubed and dot dot dot, right? Okay, we plug in 0 again, so it's g prime of 0. Now cosine 0 is 1, isn't it? And then we have a1 and everything else dies. So that tells you a1 is equal to 1. You with me? So we'll keep track of this function up here. So cosine x so far is equal to sine x. We're doing sine, not cosine. Sine x so far is 0 plus 1 times x. Good. 1 times x. Okay, we'll see what next one is. So take another derivative, g double prime of x is equal to, this is now negative sine xa. And you have this thing die, so we have 2a2, we know that's 2 factorial, plus 3 times 2, a3x plus 4 times 3, a squared plus dot dot dot. With me? So plug in 0. We have 0 again, huh? A 2a2. 2 times a2. So that tells you a2 is equal to 0 again. Huh? What's going on? This pattern is a little bit more difficult to see, eh? Okay. Now, keep going, right? Because we don't see the pattern. 0 didn't help us much. G triple prime of x. This thingy now becomes negative cosine of x. And then you have 3 factorial, a3 plus 4, 3, 2, x plus, I'm going to write one more term, 5, 4, 3, I forgot a on the other one, so I'm going to squeeze that in. Whoa, what happened? Let's squeeze. See, when you're in a hurry, this happens. So this is a4. So first so good, and then dot dot dot. So plugging in 0. This is triple prime, I forgot. So this is negative 1, now is 3 factorial a3. So that tells you a3 is equal to negative 1 over 3 factorial a. You with me? Let's box that in. Okay, I'm gonna add this thing that I forgot, triple prime. Okay, remember so far we have sine x, next one was 0, and this one is negative x cubed over 3 factorial now, correct? Do you see the pattern or not? We continue. Fourth derivative of x. This becomes now positive sine. Whoa, we have completed the cycle, right? And then we have 4 factorial a4 plus 5, 4, 3, 2, a5x and dot dot dot. So plug in 0, wrong color. G to the force 0. Now it's 0 again. So that tells you a4 is equal to 0. Okay, that didn't really work. Okay, I guess we're forced to do one more to see the pattern, eh? G to the 5th power of x. This is back to cosine, and I have 5 factorial a5 plus dot dot dot. And once I plug in 0, this gives me 1, so we're getting something. 5 factorial a5. So that tells you a5 is equal to positive 1 over 5 factorial. Let's see what we got. So this next term here is plus, oh, that thing does not look like 3 now, does it? Erase. That was cube. Still looks weird. Positive x to the 5th power over 5 factorial. Somebody predict what the next term will be. Okay, minus x to the 7 over 7 factorial. The next term? Plus x to the 9 over 9 factorial and dot dot dot. How's that? Dang. Putting it into the sigma notation, this will be, now we have to be a little clever. Right? How do you describe an odd number? That good enough for you? And then 2n plus 1 factorial. And we want to start this from 0, so that if I plug in 0, I get the first term and sign. Oh, I forgot the alternating sign, eh? Okay, so let's put that alternating sign in. Move. Okay. This computer is slowing down. Negative 1 to the nth power. Let's see. When n is equal to 0, yes, I start with a positive term. Wow. Guess what the interval of convergence of this thing becomes? It's still infinities. And you have to really put it in the graphic calculator to see this thing gives you sine x. Today's topic is Taylor series. So yesterday we found the power series representation that mimics e to the x like this, right? And that thingy was this thingy. Maybe it's a little too small for you to see. And once we graph it, this is polynomial part that goes down, and it mimics the e to the x function really, really well. Okay, and we did a similar thing with sine of x, which is right here, and sine of x turns out to be, which is right here, sine of x turns out to be this with just odd numbers, right? And here is the graph of it, right? Polynomial. You see, we didn't get a time to graph it, but if you do it on your computer calculator or Desmos, see, it follows the sine of x really, really well. And in reality, we only need it from here to here, one full period of sine of x, because anything beyond, when you're writing, after all of this is about writing a computer code, right? There's always coterminal angles, so you can actually shift it and then put it inside and compute. Good. Now, when I was graphing this yesterday, when I only put the first term, it went to the horizontal line right here, right? It was only accurate at this point, 0. And then after that, it became a line and so on. Remember that? This is known as the center of the series. And what we mean by the center is, once you plug in 0 like this, all other terms die, leaving you the constant term. Right, this polynomial. But the idea is, can we shift everything to the right by 1, to the left by 1, to the right by 2? Right? Horizontal translation is also possible. Okay, and that's general Taylor series. Now you might ask, why would anybody want to do such a thing, right? Okay, this is exactly this when you have infinitely many terms, right? But in real life, you don't have infinitely many terms. Even if you're using a computer, you have a few thousand terms, but that's not infinity. So this function, as you saw on a graph, it'll be most accurate about the center, right here. So this is great when you are trying to evaluate e to the 0.2 power. But if you want to evaluate e to the 1.2 power, maybe you want to center this thing at 1 instead of 0, is the idea. Then you don't need as many thousand terms. See, Taylor series is most accurate about the center. And it goes outward, and error gets bigger and bigger as you go outside. You get it? So that's today's topic. So today's topic is Taylor series centered at any other point, not necessarily 1. Okay, let's do that. So we're still assuming for every function f of x, in our case is e to the x, and this series representation exists. A1, we used to put x here like that, but now we are shifting this polynomial to the right by 1 because our center, we want it to be 1, okay? So plus a2 x minus 1 square plus a3 x minus 1 cube plus a4 x minus 1 to the 4th power plus dot dot dot. Good. Okay, now in order to figure out these coefficients, yesterday I plugged in 0, which was convenient, but you see if I plug in 0 here, they don't die. So I have to plug in 1. So this becomes e to the 1st power as a naught, and everything else dies. Get it? So it's a similar effect, but we are plugging the value of the center. Good. So that tells you a naught is equal to e. Good. Okay, that's one term. Okay, let's go to the next level. So we take a derivative on both sides now, on to all three sides. This is still e to the x. And first term dies, and you have a1, and this becomes 1. And then plus 2, a2, x minus 1, plus 3, a3, x minus 1 square, plus 4, a4, x minus 1 cube, and dot dot dot. Are you getting this? If you are a little confused about this, now is a really good time. And we plug in 1, so this becomes e again, and a1, and everything else dies. So that tells you a1 is equal to e as well. Good. And let's keep track of what's going on. I like to write down what e to the x is. I'm going to write it down here. So e to the x at the moment is e, first term, plus e, second term, and x minus 1. So far so good? Okay, now push this thing down. F double prime of x, we take another derivative. E to the x is a very nice function. Other functions are not this nice. Okay, so we have the first term dies, so we have 2a2 plus 3 times 2, right? Because that 2 comes down. And then a3, x minus 1, and plus this 3 comes down, so it's 4 times 3. a4 and x minus 1 square. Dot, dot, dot. Good. Say yes. So f double prime, I'll plug in 1 again, so this thing becomes e, and you have 2, a2, and the rest of the terms die. Good. So that tells you a2 is equal to e over 2. Okay, so I'm going to add it on here. So I have e over 2 and then x minus 1 squared. Good. Okay, keep going. F triple prime of x, still e to the x, and then this constant dies, so that's becoming 3 factorial now, isn't it? 1 comes down, if you will, a3 plus 4, 3, 2. After doing this for a while, this right-hand side looks always exactly the same, so you're on autopilot. Okay, x minus 1 plus, next term will be 5, 4, 3 then, huh? Okay, but on this take-home quiz, which I'm gonna give next week, you have to do this exactly like this. If you use any formula whatsoever, there's a Taylor series formula, maybe we'll get to it today. It's going to be negative 10 points. So there are only 2 problems. Out of 50, you get negative 20. I've given that kind of score before. Don't even think about using that formula. You've been warned under video. This in recording, there's an evidence. You just say, oh, you never told me. Don't say that, because then I'm going to play this video back. Okay? This is it. I have to see everything exactly like this in order for you to get any credit whatsoever. Otherwise, I don't care what the rest of the work says. It's automatically negative 20. Okay? Okay. So let's plug in f triple prime of 1. So this side becomes e, and you have 3 factorial a3, and the rest of them died. So a3 is equal to e over 3 factorial, right? Oh, maybe that tells you this thing is over 2 factorial then, eh? Okay, I'm gonna box this thing in. And then I'm gonna box this thing in. Good. Okay, so what we have is plus e over 3 factorial, and then x minus 1 cubed. This was 2 factorial. Then you can think like this. This was 1 factorial, right? Wait, 0 factorial? Did I tell you about what 0 factorial is already? Because it makes no sense, because once you multiply by 0, whole thing is 0, so what, right? For this reason, the convenience reason, mathematicians has defined 0 factorial to be 1. Otherwise, this thing breaks down, and you cannot include this first term as a part of the formula and put it into sigma notation. You get it? So this is purely for the convenience reason and no other mathematical reason whatsoever. But we can see now what an is, right? Dot, dot, dot. An should be e over n factorial. We see that pattern, eh? How about that? Good. Okay. Shall we look at this thing graphically? Oh, I have to put it into sigma notation. Dot, dot, dot. So this thing will be sigma starting from 0 to infinity e over n factorial, and then x minus 1 to the nth power. How about that? That's the Taylor series expansion for e to the x. Centered at 1. Good. Okay, let's see the graphic representation of what that is. Okay, have calculator ready so that we can compute these things, okay? Okay, so I have e to the x already, so I'm gonna graph our Taylor polynomial one by one. First thing was e, correct? For the dramatic purpose, I'm gonna add one term at a time. Now this, of course, misses it everywhere except our center. Our center was 1. See, it has exactly the correct value, e. You know what I'm saying? That's the purpose of moving the center around. Okay, now I'm gonna add plus e. What? That was dumb. E, and then I have to multiply this by our, right? Times x minus 1, right? Good. Right? So it's kind of accurate from about here to here. So this is our center. You get it? Okay, now let's add one more term. So that was plus e over 2 factorial times x minus 1 squared. Okay, there. This is my polynomial parabola. And you see it's accurate about here to about there. You see, it starts very accurate at the center and then you lose that degree of accuracy. In other words, error starts to grow and error is like not even close out here. You know what I'm saying? But we only have 3 terms. Let's add more terms. So plus e, what am I doing? E over 3 factorial. 6 times x minus 1 to the 3rd power. Whoa, look at that, huh? See, about here to about there now. And this, the region that is pretty accurate is growing. Maybe one more term. Plus e over 4 factorial, 24, times x minus 1 to the 4th power. See, it's getting pretty good already from about here to there. And this thing keeps growing outward. You get it? Okay, I'm going to make a copy of this. Okay, so we're back. I'm just going to throw it there and make it prettier later. Okay. Okay, now, then shall we develop the formula for Taylor series in general? Yeah, let's do that. Once again, we are only doing this for the theoretical purpose to give it to other people. You are not allowed to use this formula whatsoever. So if you're afraid that, oh, when to use what's the formula, what's allowed, I don't want to get -10, then don't watch this. Okay? Because whatever you don't know cannot hurt you. Okay, here we go. Oops. So we are doing this for any generic function f now. Right? So we don't have a function. It's not e anymore. You get it? I forgot to do interval of convergence, so let's do that, right? How many minutes do I have left?
10.
Oh, which one do you want? Interval of convergence or generic formula? I'll do both, and when it's time to go to the next period, you can quietly leave. How's that? Okay, so limit as n approaching infinity, and then we put exactly that, which is very ugly, gigantic absolute value, and then you put e over n factorial and x minus 1 to the nth power. That was nth. And then we put e over n plus 1 factorial here, and then x minus 1 to the n plus 1 power. Good. And limit. And then you can see that e's cancel out. You just have x minus 1 on the numerator, and then denominator you have n plus 1. Correct? And this thingy, of course, x could be a really big number all the way up to infinity, but not including infinity, as we did before. So this is 0 as long as x is not equal to infinity. Good. So your interval of convergence is all real number excluding infinities. You get it? Real does not include infinities. So it converges everywhere. Okay. Back to here. So generic function f, and we are assuming, and then some of you wonder, how can we make that assumption? Right? Rest assured, they have proven it. Taylor has proven this. So all functions have this. So you don't have to worry, wait, okay, the only requirement here is this function needs to be differentiable because we are differentiating it all over the place. You get it? Okay, and like no vertical asymptotes at the center and that kind of thing. If once you have vertical asymptote at the center, then of course it's gonna fall apart. But other than that, we're good. So we plug in wrong color. What is wrong with this computer? Change the color. Okay, now I change the color. Okay, so that's just A naught and everything is died. So A naught is equal to f of c. It's the center. And then we do it again. We take a derivative. So first term dies, so you have A1 and plus 2A2 x minus c plus 3A3 x minus c square plus 4A4 x minus c cube plus dot dot dot. Good. So you plug in your value at the center, and the reason we plug in the value of the center is that it leaves you with this constant term and all of these things die once you put c at x. You get it? So that tells you A1 is equal to f of c over 1, if you will. Okay, and continue.
Wait, shouldn't it be f prime?
F prime. Ooh, nice catch. Nice catch. F prime. This is F prime. Okay. Very nice catch. X is equal to A2 now, because this one dies. And then plus 3 times 2 x minus c plus 4 times 3 x minus c square, and then this right hand side is on autopilot now because we have done it enough times now, right? Or you will have done it enough times eventually. So that's 2 times A2. That tells you A2 is equal to f double prime of c over 2. Process continues. F triple prime of x is equal to, this thing is now 3 factorial. Do you see my mistake there? I'm missing all the coefficients again. God, this is the most common mistake that I make all the time. Okay, there needs to be A3, and then there needs to be A4 there. So whenever you try to rush things, then this happens. So now this becomes A3 plus 4, 3, 2, A4, x minus 1, and then dot, dot, dot. Good. So f triple prime of c is equal to 3 factorial, A3 and rest of them die. So that tells you A3 is F triple prime of C over 3 factorial. That tells us this must be 2 factorial and this must be 1 factorial and so on. And we see the pattern pretty easy now, right? AN is equal to F nth derivative evaluated at your center over n factorial. You get it? So our series look like this. F of x, whatever the function is, if it's differentiable and the vertical asymptotes is a nice, like, well-behaved function, will look like A0, or A0 is f of 0, or not 0, c. F of c plus f of c over 1 factorial, if you will, times x minus c plus f, this is prime, double prime of c over 2 factorial x minus c squared plus f triple prime of c over 3 factorial x minus c cube and dot dot dot. And in sigma notation, this is going to look n's from 0 to infinity. If you define 0 factorial as 1, then it will always be f of n's derivative evaluated your center divided by n factorial times x minus c to the nth power. This is the formula for Taylor series. So most books, what they do is they just evaluate these factorials and then they just attach these things factorial. I mean, they evaluate the derivatives at this center until you see the pattern, because everything else is the same. And even that is not allowed for you. You have to do it this way and this way only. You got that? So like many people, every year they say, oh no, F prime, F double prime, F triple prime, evaluate it and plug it in here. That's still using formulas. I will not take that. You understood what's required of you, what not to use, okay? Any questions? Okay, we are working towards the error of the Taylor series, error, remainder. After you truncate the first so many terms, suppose we use the first 3 terms of this power series. We have seen this one before, 1, 2, 3, actually one more here. And then whatever's left, I like to call it, so 1, 2, 3, 4, fourth degree. This means fourth degree. And then x to the 5th term and on. We like to find out what that is, okay? So let's write it here. R to the 4, which is still a function of x, looks like this. X to the 5th, it starts with the very next term. You know what I'm saying? Because when we say 4 means 4th degree polynomial, so there are 5 terms, 6, 7, dot, dot, dot. Okay, how are we going to add this? Then you're thinking, wait, this thing still looks like geometric series, correct? So we can figure out the, actually I'm gonna write down the polynomial as well. Okay, I'm gonna go down, so P sub 4 means this. 1 plus x squared plus x cubed plus x to the 4th. So there are 5 terms, like I said, right? Okay, and then this is known as a truncation error in applied mathematics, because you cannot really go forever when you write a Taylor series program. You can only use so many, right? First 100 maybe, then whatever's left, we truncated it, so it's called the truncation error. You get it? And the whole idea is you want this to be tiny, very, very small, right? You don't want this to blow up. So this thing needs to be small and converge is the key here. So how are you gonna add this? Well, we can do geometric series summation, right? Or, wait. This thing still looks like that. So could we multiply both sides by 5? both sides of this by 5. You know what I'm saying? So you want this then, or like this is also the formula you learned last year. X to the fifth over 1 over x now, isn't it? Oh, how about that? You get it? Okay. And this still is within this interval of convergence because that's where the original thing came from, unless you stretch it, well, dilate it, to call it professional term. Unless you dilate it horizontally, yeah, stretch. I mean, I can't believe that algebra book actually used the stretch and shrinkage. It's like, what? This is high school textbook. Why are you saying? And then instead of reflection, they say flip. You remember that, right? Vertical flip, horizontal flip, stretch, shrink. Like, wow. Okay, that's what the state of education is. Okay. Reflect, dilate, translate instead of shift. Okay. You know how difficult time teachers are having to adjust to that vocab from professional mathematical term to such an elementary school sounding. Oh my God. Okay. We had a meeting about it. Like everybody's going, oh my God, we have to call it a stretch and flip now. Okay. I got sidetracked. Would you like me to, since we have time, would you like me to review how to add geometric series one more time? Nah? Yeah? If you don't want to
I think we're okay.
You're good. Okay, good. So, and then this interval of convergence comes out of the geometric series summation. Okay. Now, one thing to note, because later, this one is easy because we got lucky. This is geometric series, but general Taylor series does not look like this, right? General Taylor series looks like this. There are coefficients, right? Say we use that much, right? General Taylor series looks like this. So what does this R sub R not n, let's say R4. What does that look like? Is what we are getting at. Okay, and then amazingly enough, it has something times x minus c to the fifth power in it. And only thing you don't know, you haven't learned, is what is that something here. It looks almost like, you see the next term, you get it? It only has next term in this infinitely many terms, actually can be shrunk into one term, and that's the key. We are going towards that, and this thingy is known as Lagrange error. The mathematician is a big guy. I mean, next to Newton, he might be number 2, who came up with this proof. And I will eventually prove that for you. I mean, it will take me entire period and half to prove it, but if that's coming, that's where we're going towards. Because we don't have any method for a good truncation error for Taylor series, because these coefficients do crazy things. Get it? Any question here? Taylor series, there is. Okay, so this is a good review on how to construct Taylor series the way I want it on this quiz, take-home quiz. And this is the only way I will take it, okay? So let's start. So f of x is this. I'm going to rewrite it. So f of x, which is 1 plus x squared to the 1/2 power, right? And then according to Taylor's theorem, there is this series. And we are centering it at 0. Unless otherwise specified, we are centering it at 0. But on the take-home quiz, you think I'm gonna let you center everything on 0? Yeah, don't you wish life is that easy and simple, right? Yeah, sure. And then somebody every year will always just do it at 0 anyway and get 0 point. Right? Okay. Now, so first thing is you substitute 0, right? And the reason that we substitute 0 is not because of this big side becomes 1a. The reason is the right-hand side. All those x's become 0, leaving you with the first term. So that tells you the first term is equal to 1. So far, so good? Okay. Okay, now, and then after that, in order to get the next term, we differentiate. And this is the one of the uglier derivatives. So that 1/2 comes to the front, and then we'll have 1 plus x squared to the negative 1/2 power of that negative sign. Negative 1/2 power, and then chain rule 2xa. You with me? You with me?
Yeah.
Oh, I didn't do it this way in the Dropbox note. That's why you're confused. Which way should I do it? Yeah, if I go down in this rabbit hole, I know from the experience this is one of the worst there is. Okay.
Wait, Mr. Kim?
Yeah.
For the first step, why do you add the function to the power series? Isn't it supposed to be equal?
Of course it is equal. I regret this way. Actually, this works too sometimes. Because I know for a fact this one is really hard to see the pattern. Should we just go down this rabbit hole anyway? What do you say? I'm willing to go with you. Or do it the way that I did in previous years. Or do it both ways and compare.
Can we do it both ways and compare if it's not?
Yeah, of course, that's the spirit, right? Hey, this wonderland may or may not lead to where we want to, but you'll never know until, right? And this is a good exploration. Even if we fail, you learn from this experience, and then now you will understand why I'm hesitant to do it this way, okay? This is one of the uglier things. But hey, this might be the very thing that will be on the quiz anyway, right? Yeah, let's do it. So this is a really good exploration. Let's see if we can make it. And there's no guarantee, right? We may or may not make it to the other end. What have we got to lose, right? Okay, just like another 10 minutes of our life. Okay, so there's that. When you do this, I will always like to cancel this 2 while I can, so it's not confusing anymore. Okay, on the right-hand side, so we have A1 plus 2A2. Is the right-hand side almost automatic by now? Plus 3A3, x squared plus 4A4, x cubed plus ... You with me? Okay, now we're going to substitute 0 again. If I substitute 0 because of this 2x term, the whole thing becomes 0, right? Say yes. Okay, and then we have on the right hand side A1, and that's it. So wow, why this one? How bad could this be, right? We got 2 terms already, and we only have infinitely many more left. No sweat, right? Okay, let's go. F double prime of x. I mean, this thing works, except it's difficult to see the pattern. Hopefully we will. So that now is a product rule. You see why I did not like this? Yeah, let's suck it up. So that becomes negative 1/2. And then 1 plus x squared to the negative 3/2 power a times x, and the product rule. So the other one is plus 1 plus x squared to the negative 1/2 power, and then x disappears, correct? Y'all
It's
with
times 2x, right, for the chain rule?
chain rule, that 2x, right? Yes, of course. That was a nice catch. I'm gonna go out and then put 2x. Yeah, that was a nice catch. Maybe second period is back, right? Hey, you guys have been not good lately. Whoops, wrong color. Okay, so the right hand side is equal to 2a2 plus 3 times 2a3 x plus 4 times 3a4 x squared and dot dot dot, right? Okay, let's shove in 0. So this entire term dies, right? But that one survives, and that gives you 1. And that, on the other side, you have 2a2. So that tells you a2 is equal to 1/2. Oh, nice pattern maybe? Yeah, let's go. So f triple prime of x is equal to u product rule again, right? So we have 3 over, I'm going to write it like this to develop the pattern, okay? That 3 over 2 comes to the front. You get it? And then sign becomes positive, so possible alternating signs developing here. And then 1 plus x squared negative 5 over 2 power. You know what? I'm not going to do 2 squared because I can cancel that 2, right? I should have done it while I can. So it's just the 2. Good. And then I have another chain rule. So 2x, and then I had that x here, so it's this, right? You with me? I'm just doing u prime b here, okay? And then multiply to that d. Who's lost? And this uv prime, so I have 1 minus 1 plus x squared negative 3/2, and then that thing disappears. So this is it. Good. That's just for the first term, chain rule, and I'm going to cancel this 2 while I can. Now, the second one. Okay, that one is minus 1/2. And then 1 plus x squared, and then negative 3/2. And it's chain rule, right? So we have 2x, and then 2 cancels. Dang, this is expanding, isn't it? You see why I didn't want to go down in this rabbit hole? Okay, and the right-hand side, it becomes 3 factorial. A3 plus 4, 3, 2, A4, x, dot, dot, dot. Okay, we substitute 0. Okay, so this whole thing dies, and that thing dies, so we have negative 1a is equal to 3 factorial, A3. So that tells you A3 is equal to negative 1 over 3 factorial. So that must have been 2 factorial earlier. Good. Hum, 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 hum. My other mouse is not working. I hate computers. Okay, now something is not right. I get a feeling that something is not right. We go down one more, because I don't see the pattern. It just can't be this, right? Okay. So we go down to the next level. Okay. I have that thingy, right? And wait. What does the question say? Does it say to find the fourth degree polynomial, or does it say find the general term?
Fourth degree.
Fourth degree. Oh, so we don't have to see the pattern. We can just stop it right there after this one, right? Hallelujah. Oh, thank God, because like I thought I had to find the general pattern now, right? Okay, but this is not same as what I see in the Dropbox notes. So one of the two is wrong. Do you guys see any mistakes so far?
I think A3 is wrong, but I have no clue where.
A3? Yeah, this one is not right. I'm getting a weird feeling about this.
Yeah, it should be 0.
This should be 0. Let's check our work. I think I dropped the chain rule somewhere. Okay, let's go back up here. So that 3/2 comes down. And then this becomes, number one, I already caught one mistake. Oh, 5, that's 5/2. That's correct. And chain rule 2x come out and then multiply to that thing. So that's good. And then next one is this whole thingy minus that thingy and chain rule of this. So that thing survive, and that's causing our problem. Is this term that's problematic? And then this thingy, 1/2, 3/2. I don't see what went wrong anywhere. This needs to be 0. And that kind of fits the pattern. You know what I'm saying?
I think chain rule for the second term.
This one?
Like the second part of the product rule for the first one. Like, do you have to multiply by 2x? Maybe. There needs to be an x, right? Because
yeah, but I'm differentiating this now. So the u times v prime is what I did.
Oh.
But this needs to die. That I know for a fact this needs to die, but did I screw up from the beginning? Let's go back and check.
In the second derivative, would it be 2x squared?
This is.
You know, again by the x from.
I think you're onto something. Right? So let's go back and redo this derivative, and yeah, there's a square missing. You all see that? Because there was an x already, and then I did a chain rule, so that. Wow, that was a nice catch. That tells you this one is cubed now, right? Because we have one, we picked up another one. So this is cubed. And this one has to have 2x in it here. You get it? You guys see that? That was a really nice observation. Who was it that just caught this? Who's the hero that saved the class? I'd like to know her name.
Candace.
Candace, good job. That was a beautiful catch. You guys all see that?
Mr.
Yes.
Kim, are we your favorite class again?
Number one, we, collective we, because of the one. That's a little bit of stretch. Number two, favorite is a really strong word, right? So let me just put it there. You don't suck as much. Like that. Oh, I can't believe I just said these kind of things on the recording, right? Hey, whatever. Okay, whoever is watching this video, this is not some kind of YouTube channel. This is a live class, this is a raw video. This is what really happens in this classroom. I know it's amazing. I amaze myself sometimes. Okay, we caught our mistake. Looks like, wait, we have to still make sure the second one is correct. Wait, this is 2x, so we just did that. Yeah, we're good, right? Okay, looks like we're good. If you see another mistake, let me know. So let's change all of this. Oh, this is a nice rabbit hole to go down to. And then we all have x, so this is 0 now, isn't it? And this is equal to 3 factorial. Why does that factorial look so weird? 3 factorial, 8-3. So that tells you 8-3 is equal to 0. Good. So now it fits the pattern. Now we have one more. Okay, let's be careful. After this one, we're done. We don't have to see the general pattern, okay? Thank God. So another product rule, we have 5 over, so negative, I'm going to write it like this. 5, you don't have to write it because this is the last one, that's 15, but I'll just write it that way so you can see the general pattern, okay? Over 2 and 1 plus x squared negative 7 over 2. You with me? And the chain rule, so we have 2x to the 4th power. Good. U prime v part, and then uv prime, so plus 3 here, and then 1 plus x squared to the negative 5 over 2, okay, and then that thingy becomes 3x squared. Good. Say yes. Say something. Okay, you don't see that. Derivative of that thing. Right? The rest of them is just u v prime. Okay, let's do the chain rule on this one. Okay, so u prime, so plus 3 over 2, 1 plus x squared, negative 5 over 2, and this becomes 4x squared, eh? Chain rule. And then that 2 will cancel that thingy and have us 2. Doesn't matter, it's going to die, but because we're stopping after this one. And then u v prime, so we have minus 1 plus x squared, negative 3 over 2, and times 2. Good. Say yes.
Yeah.
Okay, continuing on the next line, I'm going to bring this one to the next line because we are really running out of room here. Okay, I'm going to put them here. Push this inverse tangent down. We might be doing just this one problem, this whole period now, right? Okay, where are we? Wait, I just lost track of what I just did. Which one did I differentiate again? It's this one, right? Second part of this uv prime is that one. And then now we have to do that one. So we have to do plus 3 over 2, 1 plus x squared to the negative 5 over 2 times x. Good. U prime v, and then uv prime part. So we have minus 1 plus x squared to the negative 3/2, and then xi. So this is it. Good. Say yes. Okay. And if I forgot something, now is a good time to let me know. And next side, the other side is 4 factorial a4 and dot dot dot. You see how ugly this thing gets? And thank God we are stopping right here. We are not going to the next problem. I mean, next level. So if I substitute 0 here, and then let's see which ones die and which ones survive. This one dies, this one dies, this one dies, this one dies. These are the only 2 that survive, right? And that gives me 3. Do you see that? 2 here and 1 there. So it gives me -3. And the other side, we have 4 factorial, a4. Good. So that tells you a4 is negative. What's a 4 factorial divided by 3? Is it 8? Is it 8? Okay, which agrees with whatever is in the Dropbox note. Okay, so, and that's as far as we'll go, because I don't think we'll ever see the pattern in a million years, right? Okay, so now we can say, therefore, our f of x, which was square root of 1 plus x squared, is approximately equal to 1 plus 1/2 x squared minus 1/8 x to the 4th, and that's it. Dang, huh? Mother of all problems. Okay, decision time. We have 10 minutes left. Do you really want to go to the other one, the other way, or do you want to look at number 7 and number 9? We cannot do both now.
Can we look at 7 and 9?
Yeah, let's do 7 and 9, okay? This is what I call the microwave way. And then whatever's in the Dropbox note, I'm gonna say both versions now, right? So this is like, yeah. Okay, so, and then you guys can compare what I did. So what I did in the Dropbox note is then I didn't do square, because that square is ugly. Without the square, if you do it, then it gets a little prettier. You can see the pattern. Then later substitute x with x squared. And I'm going to demonstrate that skill here. This is a microwave way. After doing tonight's homework, you will be able to do this much. Okay, remember this will be in your refrigerator already. Some of the geometric series. You know what I'm saying? I kind of did this one for you a few days ago. Okay, now I have to build this inverse tangent. Square, x squared, and then I really don't want to. Can you imagine taking a derivative of this with a chain rule and all, and then keep going? There's no way we'll see that pattern, so we have to do microwave. Okay, first I replace x with negative x. So it becomes this. So what I have is, did I drop? That exponents are wrong. This is first, and this is square, and this is cube, right? So it becomes 1 minus x plus x squared minus x cubed. So signs alternate now. Good. Now I'm gonna replace x with x squared. Oh, did I put x squared there? X, this is what I wanted to do here, okay? And that's kind of like number 1 we just did. You figure out this thingy without the square root. You do this without the square root, then you don't have to worry about this chain rule, which is what messes up stuff. And then later replace x with x squared, kind of what I'm doing here, okay? Because that is an ugly derivative. Okay, then what we will have is x, still minus because we have just replaced the order of these replacement matters. And then plus x to the fourth minus x to the sixth. You with me? You with me? Okay, now how do I convert this into inverse tangent? You guys, some of you guys recognize it? We integrate both sides. My God. Do you remember how to integrate this trick stuff? Or you want me to show you? Why don't I show you? I'm going to do that here. So 1 over 1 plus x squared dx. Okay? We let x to be tangent theta. Then dx is secant squared theta d theta. And more importantly, 1 plus x squared becomes 1 plus tangent squared, which is still secant squared theta. Good? So this integral becomes this thingy over this thingy, isn't it? D theta. That's very nice integral, which is theta plus c. And we have to remember what theta is. We get it from here. So our theta is inverse tangent of x. You know what I'm saying? Okay, come back here. So if I integrate both sides now, then this becomes inverse tangent x, not x squared. So we still have to tweak it one more time. And let's integrate that thing. Oh my God. I'm going to start with a constant because I don't want to put it at the end of the eternity. And that thingy becomes x minus x cubed over 3 plus x to the fifth over 5 minus x to the 7th over 7 dot dot dot. So far so good? Say yes. Initial value. We have to know what that c is, right? Okay, initial value. So at x is equal to 0, the left-hand side, what is the inverse tangent of 0? 0. And the right-hand side, we have c and everything else dies. Oh, c is equal to 0. You get it? So this is 0. Okay, now, one last thing. You replace x with x squared again, and then that's what we want. So finally, therefore, inverse tangent of x squared is equal to x squared minus x to the 6th over 3 plus x to the 10th over 5 minus x to the 14th over 7 dot dot dot. You like that thingy in sigma notation while we are at it? Yeah, sure. Why not, right? So let's write it as pushing this thing down a little bit. So that thingy is, let's try to get this thing correct. Well, first of all, we are going to need something like that, right? Right. Okay, so let's look at the denominator now. We have some kind of odd number pattern, correct? So 2n plus 1, what do you say? And if I start this thing from 0, then I get positive term, so this is correct. And 2n plus 1, this is over 1. You can think like that, right? And looks like your numerator is double x to the double of this thingy, right? So we can put 2 times 2n plus 1. That makes sense to you? Let's check if this pattern is correct. So if I put 0, denominator becomes 1. I start with a positive term, and this is x squared. Yep, that seems to work. You get it? Say yes. one important thing. This thing does not converge everywhere, right? What have we done? We started with this thingy, and what was the interval of convergence of that thingy?
Absolute value x.
-1 to +1 was the only thing that was true, correct? We haven't done any horizontal stretch or shrinkage, right? We haven't done any dilation horizontally, which means if you do, you have to change that as well. So this is still only true from -1 to +1, and that's it. Wow, this is what I call the microwave way. Colin.
So like besides the problem, when we do the homework and we like derive all of the series, we can use the previous ones to get like the later ones instead of just doing the two.
Your homework tonight, you might need this skill. The reason I call this the microwave is this is the easier way of the two. Can you imagine what if you do this thing with the first problem, this method with it? Can you imagine what that would look like? This derivatives? I know it's unthinkable, isn't it? So sometimes we cannot help but to microwave. And you may do that for tonight's homework. You can use you have to derive everything. So you have to derive this thingy by the summation of the geometric series. After that, you can use that to do the next one, and then you can build it up. Okay? Sine and cosine, you have to do it the old-fashioned way, right? I did that for you. But things like ln and inverse tangent and stuff, yeah, this is a very nice way to do it. Later, fair warning, when we do something about remainder estimation, and it's called the Lagrange error, this, whatever you microwave, does not work with the Lagrange error. So this thing messes up big time. This is a price you pay for microwaving, for the convenience. It's not the same feeling as mixing the flour, marinating the meat, and do all that preparation, preheat the oven. Not the same experience. You take something out of the box in the freezer, throw it in the microwave, and you maybe put some vegetable on top. It's what we did here, and this is the easier version. Wow, this is a big boys and girls calculus. 25, let's look at 25. Let's remind ourselves what e to the x is, and we are microwaving this, so e to the x. Oh, I need to put on my work glove, 1 sec. Okay, take 2. E to the x, 25. E to the x is this. 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus, let's just write one more term. Dot, dot, dot. Good. Okay, so now e to the, of course, x over 2 is replace every single x with x over 2 then. Okay, this is just to warm you up with this microwaving idea. Good, so that's A. Now B, we have to find this looking function, okay? So B, okay, e to the x is already there, right? So let's say e to the x minus 1, right? Is equal to all of that except, oh, copy and paste. I have a computer, right? Copy and paste should work. Okay, there we go. So far with me. Then our function is divide that thing by x. So my g of x now, which is e to the x minus 1 over x. So we have 1 plus x over 2 factorial plus x squared over 3 factorial plus x cubed over 4 factorial. Okay, there's a caution. It's so much better. I mean, real mathematicians use this notation and dot all the time. Let's not get fixated in sigma notation too much, because once you take a derivative, oh, it's a whole lot of mess, okay? So like, don't use sigma notation when you do this, okay? Now, so that's B, isn't it? C is the one that you want to know, right? Oh, let's find the G prime of X, because we have G prime, eh? So G prime of X, quotient rule. Do I have to do it? So denominator squared, U prime, e to the X times X minus e to the X minus 1, and that's it, right? Okay, I have to plug in my computer. The battery is about to run out. 1 sec. Okay, computer's in. You with me? Okay, and on the right hand side, this one dies. 1/2 factorial plus 2x over 3 factorial plus 3x squared over 4 factorial and dot dot dot. Good. Say yes. Okay, now looks like they want us to evaluate this at 1. And why? Well, let's just do it and find out G prime of 1. So this thing e to the x cancels, so you have 1 over 1, so it's 1. And let's look at the other side, shall we? So we have 1/2 factorial plus 2/3 factorial plus 3/4 factorial. Do you see the pattern? Let's put it into sigma notation. So sigma of this thingy, which is what they suggest now, isn't it? 1 through infinity of, let's see what we have, n factorial, n plus 1 factorial, let's just put it like that, and then n, right? And we just have found the summation of this infinite series is equal to 1. Wow, this is not an easy thing to find, but sometimes we can use Taylor series and manipulate the function, plug in the value to find the exact value of that infinite series. You know what I'm saying? And like, don't get ideas of, oh, does that work for all series? No, you have to get lucky once in a while. Questions? Okay, let's do 26 then. So 26, I think it's a similar idea. F is that and G is integral. Okay, so let's find the first 4 terms of the, oh yeah, let's microwave this as well. Okay, because we have seen that pattern before, right? Okay, so we should remember a 1/1 minus t. That was just geometric series, right? Oh, that one looks weird. 1 plus t squared plus t cubed plus dot dot dot, right? Say yes. Now replace t with t squared and multiply by 2. So we would have 2 out here, and then 1 plus every t becomes t squared. Like that, eh? Say yes. Now integrate. Okay, so if we integrate, that becomes our g, capital G of x. Okay, now that is equal to, integrate this from 0 to x. 2 times 1 plus t squared plus t to the 4th plus t to the 6th plus dot 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 dx. Okay, let's see what we got. So we have 2, and I think we can integrate and substitute x at the same time. That wouldn't be too much algebra nowadays. This becomes t, and then x, 0, so it's x, and this becomes x cubed over 3, and this becomes x to the 5th over 5, plus, and this becomes x to the 7th over 7, right? Da, da, da. Okay, then they say first find the first 4 non-zero terms. So 1, 2, 3, 4. There you go. You get it? So this is the B part. That term. Those of you textbook reading people, McLaren. That's a car company in England, isn't it? One of the nice supercar. Yeah, same name. Well, this is okay. It has nothing to do with a car. This is the name of a mathematician. Okay. Remember, there's a power series, right? Let's just draw a little Venn diagram. This is power series. And then subset of that is called Taylor series, right? Which is mimicking the function. Subset of that is known as, God, how do you spell that name? Cool. Like that, right? It just means centered at 0. Okay, because Taylor series can be centered anywhere, but most useful one is the centered at 0, and we started with that. And mathematician named Maclaurin specialized in that type of series. Okay, not that I'm gonna quiz you on this vocab. I never put vocab problem, but if the test question or AP test question says Maclaurin series, like here, then you should know what that means. This is just a Taylor series centered at 0. You can just call it Taylor series, I don't care, but you should know what that means, okay?